All right, guys, today's lesson is congruent triangle theorems. If you've started on homework 7/8, you've already kind of learned about side, 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 and side, angle, side. If you haven't, it's okay. That's what 19 and 20 are for. So on page 19, we're going to focus on all of the theorems, and then on 20, we're going to focus on how to apply them. And then for Friday's lesson, we're going to finish up and practice proofwriting on all of this stuff. All right, let's start with the first theorem. So there are a total, looking at page 19, which all of you should have in front of you, there are 4 triangle theorems that work on any triangle. There is one that only works on right triangle, hypotenuse, leg. And then there's 2 that don't work, angle, side, side, and angle, angle, angle. So let's go ahead and start with the ones that do work. So we're going to start with the first one called side, side, side congruency. Side, side, side congruency basically states if you have congruent 3 sides of one triangle congruent to 3 sides of another triangle, then the triangles are the same. Basically what that means is, I'll zoom out just a little bit. I've got our little clicky stick things that we use for hinge theorem. If I have 3 measurements of a triangle, and I'll take these apart as well, and I want to construct 2 different triangles, basically. So I'm going to go ahead and try. I've got a pink, a green, and a red on each piece. So basically it's representing a side, side, side. So I'm going to make a triangle by connecting all of these together. All right. This is the triangle that is created. So let's try to construct a different triangle, but using the same parts. All right, so before I connected red or pink first, so I'm going to connect red first. Then I'll go ahead, sorry, it's hard with nails. Go ahead and connect this one to red and connect it this way. Even though I connected them in a different pattern, they're still identical. So what I can do is I can actually go ahead and if I overlap them, notice how they are the exact same triangle. Everything about them is identical, but I constructed them in a different way. Side, side, side congruency states if 3 sides of one triangle are congruent to 3 sides of another, then the triangles have to be identical, which we just showed using these little clicky sticks. Let's focus that on one of these triangles. So we're going to start with assuming all these triangles are turned the same way. This will make this just a little bit easier. So we'll say side A, B will match side E, D. So segment A, B is congruent to segment E, D. Next, we have BC, and that will be the same as DE. So in all these examples on this page, the triangles are going to be turned the same way. We're not going to focus on a congruency statement. We'll write that at the end. And last, we've got CA and FE. So CA is congruent to FE. Notice, and I'm going to take out some highlighters here, we've got one side pair here. We have another side pair here. And our last side pair here. So that kind of represents the side, side, side. Now, this is going to seem very strange until we kind of put it all together. So this page 19 is mostly going to be just learning all of the theorems, and just trust me when I say we're going somewhere with it. To be able to classify how triangles are congruent, you have to know all the theorems first. So I'm going to try my best to break everything down for you, but we're just going to start with side, side, side. It's the easiest. So again, we've got 3 pairs of congruent sides. I'm going to label this as a side, and side. So the letter S will stand for side, A will stand for angles. So we have 3 pairs of congruent sides. Therefore, triangle ABC is congruent to triangle EDF. by side, side, side. So I've shown that my sides are all the same, so that must mean that my triangles are congruent. So just a recap, side, side, side is whenever you have three pairs of congruent side measurements. These are all different. They could all be the same. It really depends on the type. All right, let's try 2, side, angle, side. Now, we're going to learn one new vocabulary word called included. So this angle is called an included angle. So side, angle, side. The term included means between. So basically, for side, angle, side to work, you have to have 2 congruent sides with a congruent angle in between. So let's just make this up as we go. Let's start with our first side, AB, and EF. So segment AB is congruent to segment EF. That's going to represent our first side, AB, EF. Immediately after you see a side, you must have an angle touching it. So I'm going to go to B. It gets a curve, and F will get a curve. Remember, these are turned the same direction, so we don't have to worry about a congruency statement. So angle B is congruent to angle F, and that is our first angle, and this is the included angle, meaning between. Actually, I'm going to use a different color here. For angles, I'll use a pink, but I'll use this light pink because I don't want it to be too dark. So I have my angle. Next, we'll go to our last side. So the sides must touch the angle. So 2 bars and 2 bars. Segment BC is congruent to segment FG, which is a side. This is called SAS, side angle, side congruency. Notice also you can be labeling on your picture side, angle, side. Side, angle, side is how you prove it congruent. The angle must be between the sides. So our statement, if 2 sides of end and included angle are congruent in one triangle, and then they're congruent to the other one, these 2 triangles must mean that they're the same. Side, angle, side. The angle is between the sides. Therefore, triangle ABC is congruent to EFG by side, angle, side. For side, angle, side, the angle must be between the sides. Side, angle, side. All right, let's try the third one. Remember, this will work for any type of triangle. The next one is angle, side, angle. It is literally the opposite of side, angle, side. Instead of an angle being in between, now it's a side in between. So let's start with our first angle. Let's focus on B and E. Angle B is congruent to angle E. So for angles, angle B is congruent to angle E. Now, immediately after the angle, we must go to congruent side measurements. So let's go clockwise this time. Let's go to BD and EG. So this was an angle. Segment BD is congruent to segment EG, and that is a side. So we've got BD, EG. Now, in order to find our last angle, it's actually not as hard as it looks. If you look at the way you named this segment, you actually are naming the angles. So BD and EG, notice B is congruent to E. That must mean that D must be congruent to G. So this is our last angle pair. So this will get double bars. So angle D congruent to angle G. Notice here how the angles are touching the segment. They're basically the end points of the segment. They're the end points. We've got angle, side, angle. Segment BD has B and D as its sides. Okay? And you can also label this. Curves mean angle, bars mean side. Angle, side, angle. It will spell it out for you if you label. So therefore, triangle BCD, so BCD, is congruent to triangle EFG by angle, side, angle. Notice here, again, the side is between the angles. So just bear with me. I know that I'm going through just a lot of theorems here, but we'll see how it's applied when we get to proofs, which is our last section in this chapter, which you'll learn on Friday. All right, the very last one is angle, angle, side. This one is the trickiest. The difference between angle, side, angle and angle, angle, side is the location of the side. So notice in the terminology, angle, angle, side, the side is last, meaning off to the side. So the same idea is going to exist. So let's start at B. B will go to E. So angle B congruent to angle E. That's our first angle. Then we're going to skip a side. So I'll highlight here B and E. That's our first little angle. Then we're going to skip immediately to another angle. And I'm actually going to use the same angles over here to show how it looks a little bit different. Angle D is congruent to angle G. Oh, that's not two A's, just one. Okay. So that's our second angle. Notice already how it's different from this one. Instead of the side being between the angles, the side is going to be off to the side. CD and FG. So I'm going to just flip it again. DC is congruent to GF. And that is a side. Notice the difference in the pictures. For angle, angle, side, angle, angle, side, the side is off to the side. It is not it's not in between the angles. So I purposefully use the same angles so you can notice the difference between the location. The theorem is named based on how the picture ends up being labeled. So therefore, triangle BCD is congruent to triangle EFG by angle, angle, side. In our next video, we'll talk about the right triangle only theorem, and then why some other theorems don't work, and then we'll move on to some application. But before you switch to the next video, just be mindful, pay attention to how these theorems are similar and how the theorems are different. They're very similar to each other. Side, side, side. I've got three sides. Side, angle, angle. Or, side, angle, side. I've got an angle between two sides. Angle, side, angle. I have a side between two angles. Angle, angle, side. I've got a side off to the side. So just practice. It's going to take a little bit of time, but once we do some routine work on page 20, and this is also in the packet I gave you before we left for our remote learning, all of this stuff is in here. It's also on IXL. So in the next video, we'll finish up page 19 and start page 20.